Next, we're going to look at finding the molecular formula. And so, one, we have to know what the empirical formula is first. Determine it. And then calculate the molar mass of the empirical formula unit. And that's what we're going to call the empirical mass. So this one, 3 times 19, and then phosphorus is about 31. Okay, and then we need the molar mass of the compound by. So this is telling us mathematically what we need to do to write the molecular formula. So a compound with the empirical formula C2H5 has a molar mass of 58.12. I'm not going to do PF3 one. But in PF3, this turns out that the molecules weigh the same as the imperial unit. And so C2H5. Now, the molar mass numerically is going to be the same thing as the molecular mass. So the molar mass is 58.12 grams per mole of molecule. If I had one individual molecule, then I get something called the molecular mass. The molecular mass is going to equal 58.12 U per molecule, individual molecule. Here. And so for C2H5, I have this. I have 2 carbons. 2 times 1201 gives me 2402 U or grams worth of carbon. Remember, it's interchangeable. The 5 becomes 101. It's going to be 505. So if I look at the empirical unit, it's going to weigh 07. It's going to be 2907. And so this is what we call the empirical mass. C2H5 unit weighs 2907 grams per mole or U per molecule. It turns out that this is not a molecule. If you look at the actual molecule weighs this. The actual molecule weighs 58 U, but the empirical unit weighs 29 U. So the molecule is twice as heavy. And so this is only half the molecule. Do you guys see that? This is only half the molecule. It's only half the molecule, so the molecular mass has got to be this. It's got to be C4H10. C4H10 would weigh 58 U. Okay, so what we're doing is we're comparing the empirical mass with the actual mass of the molecule. This is the actual mass of the molecule. And we see they don't match. Okay, now what your book says is to calculate this. Your book says to put it in a mathematical equation to get a multiplication factor. And so the mathematical equation is this. The molecular mass divided by the formula mass gives us the factor N equals N. Or do they call it N or X? N. And so the molecular mass is 58 over 29, 58.12 over 29.07. .12 divided by 29.07. .99993. About equal to 2 times. This is the factor that we need to multiply. Multiply empirical formula. What they're saying here. But all this is saying is that the molecule is 2 times heavier than the empirical unit, and therefore the molecule is twice as big. And therefore you need to multiply by 2, which we did here. Okay, so let's see how they completed this problem here. So you got the empirical mass. And they get the factor. So they just multiply by 2. So this out to be butane, C4H10. Might not be butane. There's tricky because that formula can represent more than one structure. All right, that's some chemical formula relationships. The next chapters are going to be chapters 7 and 8. Oh, 8 and 9, sorry, chapters 8 and 9. Look at chapter 8. Chapter 8 deals with chemical reactions. When we have a chemical change or chemical separation or a chemical reaction, what happens is you start off with things called the reactants, and then you end up with things called the product. And so in any kind of chemical change, let's say we burn methane. If we burn methane, then we get something like this. We start off with methane and oxygen, but do we end up with methane? In a physical process, we start off with methane, we end with methane. So let's say we froze methane, we get frozen methane. Let's say we would liquefy methane, we get liquid methane. But it's still methane. Its chemical identity didn't change. But if we burn methane, are we still going to have methane left over? No, we're going to have CO2 and water. And so, and this is going to be chapter 8 here. In chapter 8, we're dealing with chemical reaction. And so over here, we call these the reactants. The reactants go in, and what comes out are the products. The reactants on the left, products on the right, and then we have a little arrow showing the change, the transformation from reactants to product. When we do this, these are called subscripts. Here. These are the coefficients here. In other words, the subscripts tell us we don't want to mess around with the subscripts, because if we start messing around with the subscripts, like for example, if I change it to CH8, is CH8 still methane? No, so we don't touch the subscripts. The subscripts tell us the identity, the composition of the chemical, whether it's a reactant or product. We can't change the coefficient. So does changing the coefficient change? I mean, this is O2 is what? O2 is oxygen. But if I have a 2 in front of here, what does that mean? All that means is that I have 2 oxygens. And so methane looks like this. Methane is going to have a structure, kind of looks like this. It's kind of spherical shaped, so I'm trying to show it. This is a wedge, this is a dash. Talk more about that later. And then I have oxygens, like this. These are bonds that hold it together. We have two main types of bonds, three bonds: metallic, covalent, and ionic. When we're dealing with molecular compounds, we're looking at covalent bonds. When we're dealing with ionic compounds, we're looking at ionic bonds. But covalent bonds can also occur for things like diamond and quartz and those kinds. So we call those covalent lattices. Anyway, this 2 just means we have 2 oxygens here. 1, 2. Later on, we're going to have all these dots around here, like this. Dots are just to keep track of the electrons, which we'll talk about later. And so we take 1 methane and then 2 oxygens, and we end up with 1 CO2. A CO2 has a carbon here, and then the oxygens here, 4 dots on each oxygen, like that. And then 2 waters. So you can transform into 2 waters here. All these are covalent bonds that hold the atoms together in the molecules. These are all molecular compounds here. So methane plus 2 O2s yields a CO2 plus. Okay, now the thing is, how many hydrogens do I have over here? 4. And so I need a total of 4 hydrogens over here. And so I have it if I have 2 waters. If I only have 1 water, then it's what we call not balanced. I'm missing some atoms, so I need to put a 2, coefficient 2 here to indicate that. And then I have how many oxygens? 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, and then 1 carbon. And so basically in a chemical reaction, this is what Dalton, when we're talking about Dalton, the atoms are rearranged in chemical reactions. So this is a chemical reaction. This reaction is called a combustion reaction. Combustion. In fact, this is one method of chemical analysis. One method of chemical analysis is if you have something that you can burn, you burn it, and then you trap the CO2 in water that's formed. By trapping the CO2, all the carbon atoms that were in your original compound end up in CO2. And then we can weigh it, figure out, we know the percent composition of CO2. That's percent carbon composition. So we can get how many grams. All the grams of carbon that were in the original, let's call this unknown, end up in CO2. We know the percent carbon composition of CO2, we can figure out how many grams of carbon. And therefore, we know how many grams of carbon there were in the original unknown. All the hydrogen ends up in H2O. We know the percent hydrogen composition of water. We can figure out how many grams of hydrogen, and all of those grams came from there. So we can get the grams of carbon and the grams of hydrogen. This is called chemical analysis here. That chemical analysis we can use to generate an empirical formula. Water we can't burn, unfortunately. It's not so easy to burn water. And so water we have to use some other techniques of chemical analysis to figure out how many grams of hydrogen, how many grams of oxygen there are per gram of water. That kind of thing. It's the same type of deal we do. Combustion, this is also called something, it's also called redox. What redox stands for is oxidation / reduction. Do you know what the oxidizer is in this reaction? The oxidizer? O2 is the oxidizer. Historically, O2 is one of the best oxidizers there's around. You know, O2 is an oxidizer because what's the charge on oxygen in O2? 0. What does the oxygen like to be? -2. And so here, like if we think about CO2, we consider this, okay, if oxygen's -2, we got 2 of those. That means carbon is in what state over here? In the 4 +4 state. And so what happens is oxygen goes from 0 to -2. It's taking electrons, but who's it taking electrons from? Well, who it takes the electrons from is called the reducer. And so we need an oxidizer, which takes the electrons, and we need a reducer, which gives up the electrons. The reducer is over here, because over here the hydrogens end up being +1. If I have 4 hydrogens at +1, I'll talk about how I know that later. You might think of hydrogens as -1 because it's written, the anions typically written last. In this case, we give these plus, and there's reason for that, which is easy, but I'm not going to talk about it right now. But if all these hydrogens are +1, then what is carbon? Here. Yeah, this would be minus 4 or 4 minus. There's 4. Well, interestingly enough, what do you think carbon's charges range from, or oxidation states range from what to what? So when we look at carbon's in the middle. You know, over here on the left, what do these species like to do? Do they like to lose electrons or gain electrons? All these species here on the left like to lose electrons or gain electrons? Lose. Like, for example, sodium loses how many electrons? 1 electron to get a +1 charge. Magnesium loses how many electrons? 2. Aluminum loses how many electrons? 3. And so on. Carbon would lose how many electrons? 4. Is it easy to lose 4 electrons? No. And so this is why I don't write 4 plus, you know, because I just write the Roman numeral 4 here. I probably should write the Roman numeral here because it's not so easy to gain. The carbon's kind of in the middle because over on the right, what do they like to do? They don't like to lose. Over on the right, they like to gain electrons. So fluorine likes to gain how many? 1. So we make fluoride. Oxygen likes to gain how many? 2, so we form oxide. Nitrogen likes to gain how many? 3, so we form, what's that called? N3 minus. What's this one called? And with a 3 minus is called, well, we have oxide, we have fluoride, oxide, nitride. This is called nitride. And then we have carbon. Carbon likes to gain how many? 4, which would form, carbon with a -4 would be called carbide. Carbide. And so there are some carbides out there, like silicon carbide. And I suppose you could call this hydrogen carbide if you wanted to as well. There's so many different names. You could call this, carbon tetrahydride, you can call this hydrogen carbide, you could call this methane, you know, depending on how you look at it. But if you look at this one, this carbon has -4, which means how many extra electrons? 4 extra electrons. This carbon over here has +4, which means how many electrons did it lose? This carbon lost how many electrons in going from here to here? 8 electrons. It has to lose 4 electrons to go to 0, and then it has to lose an additional 4 electrons to go to carbon in the +4. So we lost 8 electrons. Well, who took the 8 electrons? Who took the 8 electrons? Oxygen. Each oxygen takes 2. How many oxygens do we have? We have 4 oxygens. So over here, we'll have the 4 oxygens. Here, these 2 oxygens take 2, and these 2 oxygens in water took 2. That means the hydrogens are plus over here. And so in other words, if I look at the total oxygens going here and here took a total of +8 electrons. And so we lost 8 total, we gained 8 total. This is called oxidation reduction, or redox. And so we have an oxidizer. This is our oxidizer, the oxygen. Oxidizers take electrons. These are my oxidizers. And reducers lose electrons. This is a reducer. So over on the left, do we expect them to be oxidizers or reducers on the left side of the periodic table? Oxidizers or reducers? Reducers. Reducers. Like methane. Methane's a reducer. Reducers are typically what we call electron rich. They're electron, like carbon. Carbon's got 4 extra electrons. It's quite rich, wouldn't you say? Reducers are electron rich. Metals. Metals have electrons. Metals conduct electricity. Metals have loosely held electrons. Metals are kind of electron rich. Metals are reducers. Oxidizers, on the other hand, are what we call electron poor. They want electrons. And so over on the right side here, we have the nonmetals, which are oxidizers, except for these. The last column here, these are called the noble gases, and they're happy. They have enough electrons. They don't want to lose electrons. They don't want to gain electrons. They're happy as is. And so basically, the chemical properties of the periodic table, over on the left we have our reducers, over on the right we have our oxidizers, except for the noble metals. Now, when we think about oxidizers, you know, like this is a combustion reaction, because methane is flammable. Not all metals are flammable. It depends. It's Class D fire. Flammable metals. Flammable metals are like magnesium, titanium, uranium, potassium. These are very flammable. They create a flame, catch on fire, basically. Flammable metals. Gold, silver, they aren't so flammable. It's hard to catch gold on fire. And so it depends on how easy it gives up the electrons. So rather than using methane, we could build a fire using metal. It'd be expensive fire because metals are pretty expensive, but you can build a fire using metal. In fact, when you buy metals, on the bottle, typically it says flammable, because if a metal is flammable, then there's certain things you don't want to mix with metals. For example, you want to keep the if you want to preserve your metals, you want to keep the oxidizer away from the metal. This is why, in France, this is why they have the bell jars. Do you remember the kilogram mass, that picture of it? There are like 2 bell jars. There are 2 bell jars because do they want oxygen in there? They don't want any oxygen in there, because what's going to happen is the oxygen is going to oxidize. It's not going to completely burn. It's like paper. Is paper flammable? Yeah, but it takes a long time to burn. Have you ever looked at old paper? If you look at old paper, it looks like it's charred. Because it is charred. It's charred because it's been being oxidized. And so old paper looks like it's burned, it's brown. And so this is what we're going to look for. What we're going to try to do is we're going to try to correlate properties with composition and structure. In order to do that, you're going to have to start memorizing some stuff. Some of the stuff you're going to have to memorize are like, let's start off with the periodic table. All metals are reducers. Metals tend to lose electrons in chemical reactions. Most nonmetals, except for the noble gases, are oxygen. But before we get there, we're just going to look. The easiest way to start learning about the correlation between properties and composition and structure is by taking lots of observations, right, and seeing, and then trying to build up some kind of mental database regarding this. This is an obvious chemical reaction here, but sometimes it's hard to see evidence of chemical reaction. So here's some things you look for in a chemical change. One, color change. Color change might indicate a chemical reaction, it might not indicate a chemical reaction. It depends. Change of color is very deceptive. Sometimes it could just refer to dilution or concentration. Like if you dilute soap, it's going to change its color. But is diluting soap a chemical change or a physical change? Diluting it with water. It would be a physical change. Formation of a solid product. Formation of a solid product, sometimes what happens is a solid forms from a liquid. Formation of a solid product, it could be ice. If ice forms from liquid water, is that a physical change or a chemical change? That's a physical change. This type of solid formation is different. This type of solid formation looks like this. I'll just show you. This type of solid formation is called precipitation, but precipitation could also be physical too, like precipitation, rain, or precipitation. These are the pure salts here. A lot of salts dissolve in water. If they dissolve in water, then they'll form a mixture, a homogeneous mixture called a solution. It's an aqueous solution, it's a solution with water. So the solid should completely dissolve here to form a proper, otherwise we'd call it a mixture.
And same thing with the potassium ion. Hopefully I don't make as much of a mess. Ki makes some water, also making an aqueous solution. And both of these solutions, both of these salts are soluble in water. So
we took the pure compounds and made it with aqueous mixture, aqueous solution.
You can see through them, and you can see the solids are now been dissolved. Okay? Now, interesting enough, lead nitrate is made of the nitrate ion. Nitrate ion is NO3 minus 1. And anything combined with the nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative 1 stretched over 4 atoms, so its charge density is very low. So it doesn't attract.
Let's skip that. Let's just go to the.
Spectators. 9. Like most halides, they're all actually with those. And because iodine 7.
Well, this is a combination. This one's easy to tell that there's got to be a chemical change because a color plus the formation of the solid.
Prefers itself more, or attract itself more than water. So let's do that. Here we go.
So you can see that's called precipitation. And it forms this cloudy mixture here,
Yellow.
which is actually a suspension. You know, it's like muddy water, silty water.
Yellow lead paints have been known to be yellow.
They use it for
There
pigments.
you go, there's your precipitate.
Okay. It's solid. Formation of a gas. Formation of a gas is called effervescence. So, maybe one more. So one of the most common gases would be CO2, the hydrogen gas. and
Welcome to Simple Chem Concept. This is Sean Chua. Hello?
Mute this. So let's see if we can see. Do you see the bubbles forming there? It's effervescence. We're generating a gas. It's not boiling. I mean, this is at room temperature, basically. It was that Alka-Seltzer, probably. Alka-Seltzer is chemical reaction generating gas. Okay, let's move on here. So, what was the formation of the solid called again? Anybody catch it? Started with a P. Precipitation. It's not the rain type precipitation or snow type precipitation, it's different. The rain precipitation and snow precipitation are physical. That was a chemical precipitation where we formed the solid. What was the formation of a gas product called? Effervescence. Good. Heat. When we release heat, it's called exothermic. Exothermic. Or sometimes when we absorb heat, when we release heat, it gets hot. It's exothermic. If it absorbs heat, it gets cold. It's called endothermic. So it could be exothermic or endothermic. Or it could emit light. Like if the flame emits light. Light emission. So here is a color change over time. It's going from purple to colorless. This is not a factor of dilution because the volume doesn't change. The volume stays the same, but the color just fades. So something's happening there. That's something called phenolphthalein. It's that kind of pink color. This is precipitation here, except rather than yellow precipitate, as in the video, this is a white precipitate that's forming. It's actually solid. It's suspended like this because the crystals are so small. Now, they usually don't stay like this. You have to give them a lot of time, and eventually you'll have solid cake down here. But since the crystals are so small, it takes a long time for them to settle down. The bigger the crystals you grow, the easier it is to get them to settle. It depends on how big the crystals are. What's that called again? Formation of a solid? Precipitation. Formation of a gas? That's it. That's called effervescent. Light, heat, and light. Heat, if we emit heat, it's called exo or endo? Exo. Light is just emission of light. This is emission of light here. These are phosphorescent tubes. Obviously there's something chemical happening here because these are glowing. These are just light sticks here. They're glowing. Emission of light. So those light emitter. Cold compress would be what? Endothermic. Cold compress can also be physical. You know, sometimes when you dissolve salt, like say you generate sugar water or you generate salt water, sometimes there's a little bit of heat exchange there. This is actually a physical process. This is not a chemical process because this is just dissolving a salt, like ammonium acetate or something like that, and it just generates, just sucks in a lot of heat. Sometimes the heat absorption is chemical, so sometimes it's not so clear if it's chemical or physical. This for sure is chemical or physical. This is sodium metal. And metals, are they reducers or are they oxidizers? Reducers. They'll tend to give up electrons. This is sodium. Sodium has, you know, when I think about water, this is the reaction between sodium and water. Is water a powerful oxidizer? You know, let's say I want to bleach my plants. I want to bleach my pants. I ran out of bleach. Can I use water instead of bleach to bleach my plants? No, because water is just water is a very poor oxidizer. You know, this is like the difference between drinking water and drinking chlorine. You know, which one would you rather drink, water or chlorine? Well, probably you drink both. It depends on how they purify your water. A lot of they don't do this in Torrance, but in some other water districts they use chlorine, Cl2, to kill the bacteria. And so when I was growing up, I was growing up in Santa Barbara, they used chlorine. So each time I got a glass of water from the tap, I could smell the chlorine. It didn't taste very good. But I remember it, this is years ago. Now they're switching to other oxidizers like ozone. Ozone's a pretty good oxidizer and it doesn't leave that residue or the smell, chlorine there. Uh-huh. They for water they use chlorine gas. Yeah, they would bubble the chlorine gas, or they would use like bleach, sodium hypochlorite. I was in the Boy Scouts, so we would go camping. There are different ways to purify water. One of the ways we would purify water is we'd carry a little jar of bleach. And then we put the bleach in the water to kill the bacteria and then drink it. It tasted awful still because you're drinking bleached out. You keep the concentration low, but it's better than getting sick with Giardia or something like that. The other option is to boil the water, but if you're on the trail, you can't always boil the water, so you use that. And they have bleach tablets, you can buy them and stuff like that kind of stuff. But bleach is a great oxidizer, oxidize the bacteria and kill a lot. Water is not a great oxidizer, but sodium is such a great reducer, you don't need to be a powerful oxidizer. And so water is taking the electrons from the sodium in this reaction here, the chemical reaction. They put a dye in here. The dye is something called phenolphthalein dye. Normally there's no color change like this, but they put a dye in here so they could see the color change. And sodium is a very special metal. Sodium's electrons, sodium is what you would call, even though it's only going to lose one electron, it's very electron rich. And if you think about sodium is a powerful reducer. So powerful that even something so mild like water which is extremely mild, can easily oxidize it. And so So you can't transport, if you have sodium, you can transport like steel, right? You see steel being transported everywhere. You can't transport sodium without special restrictions. And so, let's see, we have this. And so this video of some sodium disposal here. Watch this short video. Disposal of sodium. This is just sodium metal. I have it muted, so let me unmute.
30,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The amorphous chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Asset Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
So in a lot of ways, sodium is like methane. You know, methane's a good, powerful reducer. It's electron-rich. Sodium is as well. And we don't need something that's powerful. Like methane, methane's not as great as sodium because if you mix methane with water, do you expect any reaction to occur? No, and so that tells me that sodium is a much more powerful reducer than even methane is. Methane's pretty good. Reducers, we have another name for reducers. The other name for reducer is a fuel. You know, when we have a combustion reaction, we need fuel plus oxidizer. We need fuel plus oxidizer. So in this reaction here on the video, the fuel is the sodium metal, the oxidizer is water. We get the combustion there.
And actually, it's a little bit more complex than that. I'll talk about that particular reaction again later. So this is a very dangerous reaction, obviously. That's why they aren't using their fingers. You don't want to touch sodium metal. If you touch sodium metal, it'll start to cause burns because it's going to react with the water and the moisture on your skin.
It's very exothermic. We don't touch it with our fingers. It's also very prone to oxidation. You can't leave sodium metal on the counter because it will react with the air and the humidity.
You aren't going to be left with any sodium metal. Here's the reaction here.
And so we have a sodium metal solid reacting with water. So this is an example of redox reaction. The oxidizer is water in this case, the reducer is sodium. So the water is going to take electrons. Well, what in water would take electrons? Would the oxygen in water take electrons? Or the hydrogen in water take the electrons? Actually, there are two more hydrogens here. Interestingly enough, look at the hydrogens before reaction. Look at the hydrogens after reaction. Did anything happen to the hydrogens? No. Nothing happened. And so, let's see. And so let's take a look at this. What's the charge on sodium in this reaction? What's the charge on sodium on the left? The charge on the sodium on the left is 0. This is sodium metal, not sodium ion. Sodium metal. And so what we have is we have sodium 0. And then we think about this in terms of, we break down, even though this is molecular compound. Now, molecular compounds aren't made up of ions, typically, we think.